may be online, we might not be online, I don't know. I'm online. Awesome. All right, so if I go to this screen and then this screen, there's that delay. All right, might just have to turn the sound off on your devices in here so that we can do this. But welcome to anyone else that's joining us as well. So this is the first of the live streams, and I actually have no idea how this is going to go, but this is a bit of a trial today to see how it runs. So we're going to look at the notes for exercise 8.2, and I'm going to make the notes a bit bigger on the screen so that you guys can see it. So today we're looking at exercise 8.2, and it's to do with this thing called the fundamental theorem of calculus, and it's the second version of it. So yesterday we were introduced to the first of the fundamental theorems of calculus, and before we start, what I might get anyone that's online to do is just to type your name in the comments and see if it pops up on the screen as well, as a way for me to know who's here. Yeah, so also whenever there's a, hi Grace, whenever there's a question that I ask, there's going to be around about a 30-second to 40-second delay for everything that I say. So yeah, it's going to be a bit weird about that. All right, so let's just get into what we're doing today. So this fundamental theorem of calculus, the second version of it, I've posed this starting question. It says, what does your intuition say about the derivative of an antiderivative? So that's what we're going to look at as a mini investigation. We're going to look at what happens when you look at the derivative of an antiderivative. So let's start off with this original function. Let's say if our starting function is 3x squared, f of x is equal to 3x squared. What we're going to do is we're going to anti-differentiate that first, because that's what the bit on the top says. We're going to do the bit inside the brackets, we're going to do the antiderivative, and then we're going to do the derivative of it. So if we anti-differentiate 3x squared, we add 1 to the power, we divide by the new power, and we end up getting x cubed plus c, x cubed plus c. All right, so what happens now if I differentiate this term, x cubed plus c? So when I differentiate it, just to apply the normal rules, that's where the power comes out the front, so that's where the 3 comes from. The power goes down by 1, and the plus c disappears because it's a constant. So what have we just done? We have just gone full circle. We started with this original function, we anti-differentiated it, and then we differentiated it, we got what we had to start with. Kind of makes sense. So taking the derivative of an integral gets us back to the original function. It's all because those two things are complements of each other. They are opposites in a way. So if you do the derivative, it's the opposite of antiderivative, and vice versa. Inverse functions. Okay, so let's talk about this fundamental theorem of calculus, the second one. All right, so to start this, we're going to think about what this graph is on the left-hand side. So we're going to start with a random graph, and we're going to call it f of t, and it's this kind of cubic-looking graph like that. We don't know the equation of it, it's just got that random shape. And suppose we're really interested in looking at the area function of this red shaded region. So we're looking at this area function, and this red shaded region is somewhere between A and B. As we move from left to right, this x value is changing, okay? So we want to look at what happens to the area underneath this curve as this x line changes from left to right. As it's moving from left to right, what's happening to the area as we progress from left to right. So we can write the area function like this. So a of x stands for the area function. And we learnt from yesterday we can do this, right? This is a definite integral from a to x. And the x is changing. The x is moving from left to right. And the function is the graph that we had to start with. And dt is just with respect to what variable we're choosing. So the x value is somewhere between a and b are constant values, okay? So at the moment it looks like a, in this example we've got a is equal to 0. It's like right on the origin point there. but B is somewhere in the distant side over on the right-hand side. So as we can see here, as x increases from left to right, the area underneath the curve is going to increase, okay? So at the very beginning, if my x line there was right on the y-axis, on the f of t axis, the area function would be 0. And as this area progresses, as we fill in more space from left to right, the area function increases. The area underneath the curve gets bigger and bigger. The other thing that I need to note for this particular example is no part of the graph is below the x-axis. So the integral, there's no negative integral. There's nothing below the x-axis. So everything here underneath the curve is going to be a positive area. Okay, and the other final thing I need to talk about is this thing is continuous. There's no breaks in the curve. There's no gaps. This is a continuous function from A to B. So what if we wanted to work out the rate at which this area function is increasing? Okay, in other words, we're working out this a dash of x, the derivative in a way. We're working out the rate at which the area underneath the curve is increasing with respect to the area. So is this constant? So as we go from left to right, is the rate at which the area is increasing constant? No, because you can see the area is increasing quite a lot up here, where the graph is quite high above the x-axis or the t-axis. And as the area progresses through underneath this low section, the area function is going to be not as increasing as much. It's still increasing, but the rate of increase is not going to be as much. So definitely it's not constant as we progress from left to right. Okay. So to investigate this further, let's take a close look at the changing value of x. So we're going to look at this we're going to zoom into this section here. We're going to find out what's happening to this area function if we were to just look at a small snippet. So let's think about a rectangle. So if we were to split that red section up and draw a green rectangle, okay? A green rectangle, and just going to look at the rate at which the area is changing just in this section alone. So the width of the green rectangle is delta x, okay? So that's just how much x is changing within that period of time across the horizontal axis. So the width is delta x. The area of this green strip we can say is equal to the area function from the very beginning all the way to x plus delta x, so all the way to this line here. So if I draw in another solid line, so if we look at the area of the green section that we want, it's the red section plus the green rectangle. So that's what that area is, the area function x plus delta x. So it's this red section plus this bit. And then if we take away the red section, that's going to give us an approximation of the area of the green part, okay, the green rectangular strip. So what we're going to do now is we're going to do even more of an approximation. We're going to break this up into a smaller estimate of the area of the rectangle of the green strip and a larger estimate, an overestimate. So if I draw a line here across from f of x, just across here, this section below that line would be an underestimate of the area of the rectangle, and this line above it would give me an overestimate. So the area of the green strip that we want is going to lie somewhere in between. It's going to be bigger than the area of the underestimate, bigger than the smaller rectangle, but it's going to be smaller than the bigger rectangle at the top. It's going to be somewhere in the middle there somewhere. So what we can write down, this gets a bit weird, a bit complicated, but it does get to my point eventually. So the area of the underestimate of the rectangle, so this smaller rectangle, is equal to the width, so delta x, times the height of that rectangle, which is f of x, okay? The area of the overestimate of the rectangle is this thing over here. So the height of the bigger rectangle is f of x plus delta x, and the width is still delta x. And the area of the green strip is what we talked about up here. It's the area function of x plus delta x, so it's the entire area of that section, so red plus green zone, minus the area of the red section there, okay? So that's what gets you the green strip. So this area of the green strip is going to be somewhere in the middle. somewhere in the middle, and you can kind of see it's pretty close to halfway in the middle because the graph line goes almost cutting through those two sections of the rectangle part up there. All right, so let's do a bit of algebra manipulation to this inequality. So what we're going to do is we're going to divide everything by delta x. We've got a delta x common to the area of the underestimate and a delta x common to the area of the overestimate of the rectangle. So if we divide everything by delta x there will cancel each other out. The delta x here will cancel each other out. But this middle term, this middle function, will have a delta x on the bottom. And we've seen something very close to that before when we're dealing with derivatives. So what we're going to look at is we're going to get a better approximation of the way this thing is changing if we limit this delta x, and we look at how this delta x gets closer and closer to 0. So if we reduce delta x and make this rectangle as skinny as we can, as close to 0 as we can, we will say the limit as delta x gets to 0 of our middle section here, the area of the green strip, is going to equal, well, if I look at this, if I make this delta x as close to 0 as possible, we're going to end up with this thing here. It's going to be a rectangle so thin that it's basically just going to be a line that is the height of f of x, okay? So if I reduce delta x, this green rectangular section, and I make this delta x as close to 0 as possible, I'm going to have a rectangle so thin, so narrow, that it's essentially just the height of f of x, that section there, for that red line that I've just drawn in. Okay, that's what this bit here means. So it's just this highlighted yellow section there, okay? So we understand from derivatives, differentiation, that this thing here is like from first principles. The limit as delta x approaches 0 of our function x plus h. Remember the one with h approaching 0 minus f of x over h? So this thing here is exactly like differentiation. So this thing is exactly like differentiation. It's the rate at which a is changing with respect to x. So what we're saying is this thing here, the derivative, the rate at which the area function is increasing is equal to f of x. It's equal to the height of my graph where x is, wherever x is on my graph, okay? So we can write it like this. The derivative, the rate at which the area function is changing is equal to f of x. The area function is that integral that we had at the very beginning, the integral from a to x of f of t dt. So therefore, putting those two bits together, if the area function is the antiderivative from a to x of our function, we can put that into there. So it's d dx of our integral is equal to f of x. It's the fundamental theorem of calculus. So it's the rate of increase of the area function is approximate to the value of f of x at the time. So if we scroll back right to, let's go to this graph here. Let's go right back to here. So what we're saying is, as the area function goes from left to right, as we move this x value anywhere between a and b, and we look at how the area function is increasing, we're looking at the rate of increase of the area function. It's equal to whatever the height is of the graph wherever x is. So if x is there, the rate of increase is just going to be whatever the height is of the graph at that point. It's just going to be f of x. It's just going to be what that point is. If x is over here, and we work out the area in this section here, and x has moved to that point, the rate at which the area function is increasing is equal to the height of the graph at that point. It's just equal to f of x, okay? So if I just undo that. All right, so if we go down to this rule, it's saying the rate at which the area function is increasing is equal to the height of the graph, f of x at the value of x. And that's the fundamental theorem of calculus. That's the second one. All right. So how do we apply it? How do we use it for these examples? It kind of goes back to the intuition idea. So when you take the derivative of an antiderivative, you get left with what you have at the very beginning. And so in this first example, I don't want you to anti-differentiate this thing. I just want you to apply the fundamental theorem of calculus. Okay, so I'm just going to zoom out so we can see it again. So we've got the derivative of our function, our antiderivative, so the rate of which the area function is changing, is equal to f of x. So all we're going to do, this is our f of t function. All we're going to do is replace the letter t in our equation with x. Just going to drop that in there. That's all it is. Okay, so we're replacing t with x. So the rate of which the area function is changing is equal to 3x minus x squared, because that's what the height of the graph is where x is at that time. That's your f of x value. Okay. The question is, does it matter what a is? Does a have to be a particular number for this to work? Like, does a have to be 0 or does a have to be 1, this lower limit value? So let's test it out. So let's try on our calculators. So we've got to get our CAS calculators out, or Casio calculators if you've got Casio. And we're going to type this in. So we're going to go ddx, and we're going to go open bracket, and we're going to type in this integral. Keep in mind the use of the letters. So you must use an x to start with, because we're working out the rate at which the area function is changing. That's what we're dealing with here. And we're looking at it in respect to x, where the x value is on our graph. And I want you to type this in on your calculator. So I want the integral between negative 34 and x, and 3t minus t squared dt. Remember, this function here is the initial graph. It's f of t. It's how the graph is changed. This is like a upside down parabola. That's okay. So I want you to work out if it gives you the same value as what we had up here with an a value of 1. Let's have a look what happens. So if I jump out of here and just going to go to my desktop. Let's do it on the TI, even though it's the same idea. While that's loading. Okay, so what I might do is I might just get this as a smaller version of this again. Here we go. Okay. All right. So hopefully you can see that one okay. So on the TR calculators, you get the book of functions down here. We're going to use this a lot. And it's going to be this thing here. So we're going to go ddx, and inside the brackets, we're going to go book of functions again, and we're going to go with this integral. But this one, make sure you use the definite integral one, the extra boxes on the top and the bottom. Pop that in. And so we're going to try this. Negative 34 all the way up to x, and we'll go 3t minus t squared. And we're going to go dt in there. See how it says 3x minus x squared, which is what we had before. Let's try it and let's put a different a value in there. Let's put in a different value. Let's put in, I don't know, 71. 3x minus x squared. It's independent. It does not matter what your starting value of a is, because when we were doing our working out before, if we go back to all this random theory stuff, at no stage in our working out over here were we actually referencing this point A. It's all to do with this green strip, which is in the middle of our graph somewhere, and not actually our starting value, or even our end value, B over here. Well, they're independent. So this method, this thing, works no matter what the starting value is, no matter what the constant value is. Okay, so the next example we're going to do is we're going to look what happens if we mix things just up a little bit. Okay, so we're going to be looking at the rate at which the area function is changing, but this time we've got the integral going between x and 3. And we're using u's this time instead of t's as well, just to make it a little bit different. So with this type of setup, the first thing we want to do is whenever you want to flip the lower and upper limits of an integral, what you have to do is make your function negative, your integral negative. So the way we're going to do it, so if we've got a at the top and b at the bottom, if we want to make the a at the bottom and b at the top, so we're basically flipping the upper and lower bounds, we need to apply the negative to our integral, okay? So let's do that first. So let's apply a negative to this rule at the top. And then once we've done that, once we've got it into the right format so that the x is at the top and the constant is at the bottom, then we can apply the fundamental theorem of calculus idea, okay? So let's do that. So I'm flipping the 3 and the x over, but I'm making the whole thing negative. By doing that, all you do is you apply this negative to the values on the top of our fraction, okay? So 1 minus u, when I multiply it by -1, makes u minus 1, okay? So now it's ready to go. All we need to do now is apply the fundamental theorem of calculus. So that just means replace the u with x. Replace the u with x. Anywhere you see a u in here, replace it with x, because that's what the result's going to be. It's going to give us the height of the curve when we get to the x value, okay? And that's it. X minus 1 over 1 plus x is your answer. You don't have to do any more to it. You don't actually have to anti-differentiate or do anything. You just leave your answer as that, x minus 1 over 1 plus x. All right, pretty straightforward. So next, we're going to make things a little bit trickier. So instead of just a straightforward x at the top, we're going to change it to square root of x. And before we actually do this this question, let's go back to this example here. So if we checked out the first example, it didn't matter what we put in for that lower number for a. Like we could put in any number we liked and it still spat out 3x minus x squared. But what if, let's go back to putting in a nice number because that doesn't make any difference. But what if instead in the top, instead of writing from 1 to x on the integral, what if we changed it to 1 to 2x? So we changed the upper bound, instead of just being a straightforward x, what happens if we change it to 2x? And let's just check that out. So you'll see here that it's very different. It's not the same anymore. So changing the lower bound, changing that constant makes no difference, but changing the upper bound, changing this thing makes a big difference. So what we're actually saying here is we're looking at the rate of increase from when we're going from 1 to 2x. So if we go back to my OneNote notes, it's as if we were to go back here and say, all right, I'm going to look at this function and we're going to say, here's my original x value, somewhere between a and b, all right? How's the rate of increase of my area function going to go when I take this thing and I put it to 2x, maybe around about there, that part of the graph. So I'm going from a to there. So it's not going to be just the straight up function f of x anymore. We've got to do something a little bit different to it. We're basically going to have to substitute whatever the value is in here. So if it's 2x, we have to substitute 2x into our function. Okay, so that's pretty much all we do. So we replace the thing with 2x, double it. We times it by 2. So over here, so we replace x with 2x. So, and then we see what happens here. Whoops. Okay, going back to this one. So what we're doing is we're multiplying by the derivative of the top thing. So it's a bit like using the chain rule. Okay, so can't just substitute square root of x into here straight away. We still do that, but then we multiply the result by the derivative of the upper bound as well, okay? So we've got e to the square root of x all squared. So just replacing the t with the upper bound just like we did before. But the final thing we're going to do is we're going to multiply the whole thing, our substitution, by the derivative of the top function. So that becomes e to the x on the top, because when you square root of x squared, it becomes just x. And the derivative of square root of x is this thing over here, 1 over 2 square root of x. And if I was to multiply these two together, you get the square root of x times the square root of x on the bottom is just x, and 3 times 2 is 6. So whenever you've got a function where you've got an upper bound that's not just a straightforward x, we always should multiply. We should substitute it into our function and then times by the derivative of the actual upper bound. So if we go back to our example over here, if we substitute 2x into our function for t, so it will be 3 lots of 2x minus 2x all in brackets all squared, and then you multiply the answer by 2, that's where you get this thing, 12x minus 8x squared. Okay, so got one more example to go, and then we'll see how we go. So this one here. So this one is where the difference in this one is this time we've got the integral between x and x plus 2. So notice there's no constant anymore. We've got variables on the top and the bottom. But this is the big difference. We've got the derivative part inside the integral this time. So we've got the integral on the outside and the derivative part on the inside. So how does that affect things? So let's try it out with our little mini example here first. Let's do the derivative of what's inside the brackets first, and then we'll anti-differentiate this thing and see what we get. Okay, so let's try that. So d du of 1 plus u cubed is 3u squared. So it's just the derivative of what's inside the brackets. But now we're going to apply this definite integral to this, 3u squared. So what does that mean? So that means set it up like you've got here. And this time we can't just apply the fundamental theorem of calculus, because there's this actually means a completely different problem. This is not really looking at the rate of which the area function is changing. This is looking at the derivative of a function first, and then we are applying the antiderivative to it afterwards. So it's not really a fundamental theorem of calculus problem. So once we've done the derivative and now we've got to apply the antiderivative, so we add 1 to the power, divide by the new power, we get this thing. And this is what we learnt yesterday in terms of substituting in the upper bound into here and substituting in the lower bound into here and subtracting them away from each other. It's quite different to as if we were to do at the very beginning, just substitute in the upper bound and then times by the derivative of the upper bound. It just doesn't work. So this is not the same as the fundamental theorem of calculus. So if you get questions like this in the exercise, just be careful. You have to do it this way. You have to do the derivative first and then substitute in the upper and lower bounds into it. So there's no short way of doing that one. Okay. This one here, I just want to do this last one to show you that you have to be careful as well. So this one, there is no lower and upper bound. So it's just saying the integral of d dx of this thing here with respect to x. So for this one, you have to think about how this is working. So it's basically the derivative and then the antiderivative, which is what we end up starting with. But when we do it, if I was to take this and take the steps of it, so if we do the derivative of this thing here, it becomes 3x squared plus 5. There's no plus c's, because when you do the derivative, there's no plus c. But now if I was to apply the indefinite integral, because we don't have any upper and lower bounds to this thing, we're going to have to add 1 to the power, divide by the new power, so it becomes x cubed. That becomes 5x. And because there's not an upper bound and a lower bound, we're going to have to put in a plus c, because we're just essentially just doing an indefinite integral here. There's no substitution required. There's no area under the curve bounds that we're dealing with. Okay, so if you get a question like this with no upper or lower bounds, it's what we had to start with, but with a plus c at the end. Okay, and just going back to this one, if you ever get a question like this, you first differentiate the function and then anti-differentiate it by substituting in the upper and lower bounds into the value. Okay, so that's it for the lesson. And what I'm going to do now is on sector, you can ask questions on there in the forum, as well as in this live feed. So I'll leave this live feed running for a bit longer. And as I said, if you've got any questions with what we've done, you can just type them either in the comment section or jump over to Sector if you don't want it to appear on YouTube. And then I will try my best to answer them, and we'll see how long we can go for this for, maybe another 10 minutes or so. And then the questions I want you to do in this exercise are, just get it open here, 8.2. So always, I'll write the questions at the bottom of the notes, so in OneNote, so you can find it. So exercise 8.2, it's on page 81. Okay, so I want you to do a bit of practice with these, and these don't take particularly long to do, and the way OTLE does them is he mixes them up quite nicely. So maybe do every second one in question 1, so all the way to there, and then question 2, same thing as well, A, C, E, and then question 3, it's a good one, and then maybe question 5, and question 6 is a good one to look at as well. All right, so I'm going to leave that there. And as I said, if you've got any questions, you can type them into the comments, or we can go into sector as well. So I will, how am I going to do this on my screens? I might just do this. Hold on, I'm just going to do this on this for the moment. I'll be right back. And then where is it? Go here. Okay, so there's nothing in there. Maybe if I just go. Maybe if I just go. All right, so it doesn't look like there's any questions on here, so I'm going to end this stream, and we'll be back again on Friday.